Imagine you live in Sumeria more than 5,000 years ago. Instagram, analytical chemistry, or hospitals aren't even a thing. You got sick, and let's suppose you have fever. The local doctor will give you bark of this tree. And believe it or not, it will help a lot. That's because this bark contains a compound called salicin, which glucosidases metabolize into salgenin. Salgenin is oxidized by alcohol dehydrogenase into salicylaldehyde, and salicylaldehyde is oxidized again by aldehyde dehydrogenase into salicylic acid. Salicylic acid is the main character of this video. It is a metabolite of the more known NSAID, aspirin, or acetylsalicylic acid. Other NSAIDs are naproxen, ibuprofen, ketorolac, celecoxib, or diclofenac. They act by inhibiting cyclooxygenases and thus prostaglandin synthesis. Here you can see salicylic acid bound to COX-2. Salicylic acid, besides its pharmacological activity, has a lot of useful applications as a building block, for example, in the mesalazine synthesis, first the nitration and then the reduction. In another example, diacetation of the compound A is made, and after azocoupling with salicylic acid, the product valsalicide is synthesized. For this video, we're going to hydrolyze the ester acetylsalicylic acid using sodium hydroxide to yield salicylic acid. This will be the first of 3 videos where I synthesize picric acid, or TNP, from a pharmaceutical product, aspirin. The explosive trinitrophenol or picric acid could be directly synthesized from aspirin, but I need the salicylic acid for other reactions, for example the esterification into methyl salicylate. With all that being said, let's start. The first thing you need is aspirin, a lot of aspirin. First, pop out all the aspirin tablets from their blisters and place them in an adequate beaker. I got 100 tablets of 500 mg each, or 50 grams of aspirin in other words. Then, pour them inside a very large round bottom flask. Then add 300 ml of acetone. Next, I moved and chopped as much as I could the tablets using a glass stirring rod, but this is optional. I settled things into reflux and added 50 more milliliters of acetone. The total volume of solvent was 350 ml. The reflux was kept for an hour, and after that the solution was let cool into room temperature. Then, a vacuum filtration was performed in order to remove the insoluble excipient. I used small volumes of acetone to rinse the flask. Here you can see the excipient, and here the acetone solution containing the aspirin. I settle a fractional distillation apparatus to remove all the acetone. After some minutes, aspirin crashes out of solution and crystallizes. Here we can see the aspirin and the acetone distilled. In the meantime, we're going to prepare a solution containing 33.15 grams of sodium hydroxide dissolved in 250 ml of water. Pour this solution into the aspirin and settle things into reflux for 2.5 hours. While this is reacting, let's discuss the mechanism. First, aspirin deprotonates on the presence of sodium hydroxide. Then sodium hydroxide attacks the carbonyl of the ester group and breaks the pi bond into the oxygen atom. The negative oxygen atom forms a double carbon-oxygen bond, kicking away disodium salicylate and forming acetic acid. A proton transfer between these two occurs, and after acidic workup, we yield our final salicylic acid. After reflux, let cool the solution back to room temperature and slowly add 28% or any concentration works of hydrochloric acid. While adding the hydrochloric acid, you will notice the salicylic acid precipitating out from solution. That's because sodium salicylate is very soluble in water, while salicylic acid isn't. Add enough hydrochloric acid till the pH is around 1. And that's it. We no longer have acetylsalicylic acid in this flask. We have salicylic acid. I filtered the solid using vacuum filtration and rinse it several times using small amounts of distilled water in order to remove all the water-soluble impurities. The next morning was a little bit cold, so in the filtrate, these beautiful looking needles of salicylic acid appeared. I filtered them separately and placed them in the crystallization dish. I transferred all the solid into a large beaker and rinsed the filter using distilled water. I start adding distilled water to perform the recrystallization, but salicylic acid never fully dissolved, even when I add more water and more water and more water. It only formed like a crust on the upper part, and those crystals fall back into the solution, so I surrender and remove the beaker from the hot plate. Crystals of salicylic acid start forming immediately. I place the beaker inside the fridge for something like 2 hours, and then I begin to filter them under vacuum. It's very important to give several rinses with distilled water. Then I transfer all the crystals into the same recrystallization dish. Here you can see the wet crystals. They have a very lumpy aspect. I dried the crystals at 100 degrees Celsius for something like 2 hours, and after that time, I got these gorgeous looking crystals of salicylic acid. They are just beautiful. I weighted all the crystals, and at the end I got 36.38 grams of salicylic acid, which represents a quite impressive yield of 94.9%. This yield is amazing because we extract and hydrolyze aspirin, and there are losses in every part of the process, so I'm pretty satisfied with the results. To finish the experiment, I did an experimental melting point test, and it resulted to be between 158 and 159 C, which is pretty accurate with the theoretical value. So that's it for today. Thank you for watching, please subscribe, and see you in the next video.